All right, everybody here, everybody at home. This isn't going to be an ed puzzle or something for anyone, but here's the notes. Here's me lecturing the notes on radiation. So if you're at home and you haven't got to have class, you may want to watch this video. Here we go. So we already did a worksheet yesterday with alpha, beta, and gamma math. And we'll have another one today. But I want to show you a little more detailed, some more detailed aspects of alpha, beta, and gamma radiation. And I want to remind you that this is Marie Curie, and she is basically the mother of radiation studies. She's the mother of nuclear chemistry. And we had a video on her yesterday. There are many videos on her. The video that we watched was from Crash Course Chemistry on radiation. So you can type in Crash Course Chemistry and Marie Curie, and it'll come right up. There's another video on Marie Curie for Great Minds from SciShow, SCISHOW. She's just an incredible person. All right. Now, the strong force is what holds the nucleus together. And if you think about it, the nucleus of an atom should not stay together. And the reason it shouldn't stay together is because you have positive protons packed into a tiny space. And like charges should repel each other. So the nucleus of all atoms should just instantly fall apart. And the only reason it doesn't is this mysterious force called the strong force, which is carried out by these particle carriers called, force carriers called gluons. And I can't tell you any more about the strong force other than the particles associated with it. The force carriers are gluons. And secondly, the strong force is very much like a spring. The further you pull on it, the stronger it gets. And this is the mysterious force that holds the nucleus together. And it's very often represented by like just drawing like a spring in the nucleus, okay? Now, the nuclei of atoms fall apart. If we look up here on the periodic table, all of these atoms can spit out protons or accept protons sometimes and turn into different atoms. And it happens quite often. Some of these atoms fall apart and change into different atoms more frequently than others. And ones that do it very frequently we consider to be radioactive atoms. Now, there are many different versions of all these atoms, and the different versions are called isotopes. And we talked about isotopes earlier in the year. But if you have an atom, for example, like lithium, which has 3 protons and normally 4 neutrons, then it would weigh 7. That's the lithium from the chart. Now, if lithium had an extra neutron, then it would weigh 8. It would still be lithium. It would still only have 3 protons, but it would be called lithium-8. So that's what isotopes are. Now, small atoms need about a 1-to-1 ratio of neutrons to protons to be stable. And larger atoms, when they're stable, their ratio is just about 3-to-2. Okay? And if you get off from these ratios very much, then you end up with unstable radioactive atoms. There are 3 different ways that atoms can fall apart: alpha, beta positive, and beta negative. And then the third thing that happens while these particle changes are happening is that gamma rays are given off. Gamma rays are just invisible rays of energy that are very, very powerful. They're even higher frequency or shorter wavelength than X-rays. Gamma rays are the most powerful rays that we know about on the electromagnetic spectrum. Okay, alpha decay looks like this. An alpha decay, an alpha particle is a big particle. It's made of 2 neutrons and 2 protons. So if a nucleus of an atom spits out a hunk like this, then it loses a weight of 4, and it loses an atomic number of 2. So an alpha particle, if you think about it, is just like the nucleus of a helium atom. All right? Now, alpha particles, here's something we didn't get into yesterday. Alpha particles are big as far as nuclear particles are concerned. Alpha particles are so big that they can be blocked by paper suits. Now, I have a buddy that works in the nuclear power plant in Southport, and he very frequently has to put on a paper suit to just walk through a certain part of the plant. And then after he goes to that part of the plant, he takes the suit off and throws it away. Does anyone have any idea of where these guys are by looking in the background? They're in Russia, in a city called Chernobyl. Have you ever heard of Chernobyl? There was a very bad nuclear accident there in the 1980s, and this town is now abandoned. There's many, many things online about the accident at Chernobyl, but basically they had a nuclear power plant which had a reactor meltdown, and it killed many, many people and ruined the town for a long time, and the town is still abandoned. Okay? And these guys are walking through, and this is, does anyone know what this thing is called? It's called a Geiger counter, and they're using a Geiger counter, and I'll show you one of those in class later. All right. Now, when atoms change into other atoms, that change is called a transmutation, okay? And we didn't talk about that yesterday, but that's the word. It's called a transmutation, okay? And a really famous, popular alpha decay that we discuss is when uranium-235 decays into thorium-231. If you notice, the weight goes down by 4, because that's how big this particle is. And the atomic number goes down by 2, from uranium number 92 to thorium number 90. So you'll see this is written 4 over 2 alpha plus plus. It weighs 4. It's got 2 protons. It's an alpha particle, and it has a charge of plus 2. Why does it have a charge of plus 2? It's got 2 protons, and there are no electrons. Okay? Often you'll see 4 over 2 He written, because an alpha particle, again, is just like the nucleus of a helium atom. Let's move on. Now, there's beta positive and beta negative decay. We've done the math on them, and we've talked about why they happen, but I'll mention it again. In beta negative decay, a neutron turns into a proton. And as it does, in order to become positive, it has to spit out a little negative. So when a neutron turns into a proton, it spits out an electron. That's how it becomes positively charged. On the opposite end of that spectrum is beta positive decay, and that's when a proton turns into a neutron. For a proton to become neutral, it has to get rid of a little positive charge. And what it spits out is a weightless positive charge known as a positron. Now, if I wanted to mess with your mind, I would tell you that a positron is an antimatter electron. And then I would hit next slide, like that. All right. So here's beta negative happening. Carbon-14, and we'll talk about carbon-14 later today, turns into nitrogen-14 through beta negative decay. All right? Carbon-10 turns into boron-10 through beta positive decay. And you'll have another worksheet. I'll try to solve a worksheet online with you, okay? All right, let's keep rolling. Now, beta particles. I told you that alpha particles can be blocked by paper. Well, beta particles can be blocked by aluminum foil, or they can be blocked by wood. Beta particles, remember, are basically beta negative particles are electrons, right? And they can be stopped by little sheets of metal or even wood, like a sheet of plywood. Okay? But The most dangerous thing that happens when atoms undergo transmutations is that gamma rays are given off, okay? And they're very concentrated waves of energy. They have higher frequency and shorter wavelengths than the microwaves that cook the food in your microwave. As a matter of fact, microwaves aren't even that powerful, right? The most powerful rays, when you get below visible light, you have UV, then X-rays, and then gamma rays. Gamma rays are the most dangerous, okay? Here's the electromagnetic spectrum going from the longest radio waves all the way up here to the shortest gamma rays, okay? So gamma rays are the most dangerous. Gamma radiation occurs anytime alpha or beta decay occurs. And to block gamma rays, you need thick blocks of lead or concrete, okay? Now, if you notice, the power plant in Southport is made out of concrete, right? Nuclear power plants are made out of concrete. One, to make them strong buildings, just in case there's an earthquake or something crazy that happens. Two, to block any incidental radiation that could occur, all right? We actually end up using water to block gamma radiation and particle radiation from spent uranium. And we'll talk about that a little bit later. I don't know if that'll make it into the video. So here's an example of beta negative decay occurring, 0 over -1 beta, right? This is an electron. And this is cobalt turning into nickel. Well, as this beta particle is given out, you have gamma rays are also emitted. So there's an energy that bursts free from this atom. And the gamma ray is what's dangerous. It's not necessarily the beta particle. We can take care of that pretty easily. All right, and here's the quick review. And this is all in your notes online, the quick review of the 3 types of decay. And what we're going to do is we're going to, I'll work a problem really quickly with everyone, and that'll be it. Okay, let's see here. How about we do alpha decay? Let's do an alpha decay for somebody. How about, what if we had carbon? Nope. How about we had, what if we had, nope. I'm trying to think of somebody I can get to alpha decay real quick. How about we had, no, I don't like that either. Well, we'll do it. Zirconium 92. 92, whoa, that doesn't work. $92. Ha ha ha. 92 over 40 ZR. Gosh, I hope you can see this at home. It's going to lose an alpha particle, which is 4 over 2 alpha plus plus. What else could we write right here instead of alpha? You're right, we could write HE, same thing. So it would turn into 92 over 40 zirconium would turn into 88 over 42 over 38. Let's see, that will be strontium. So this is the alpha decay of zirconium 92. I don't necessarily know that zirconium 92 would alpha decay, but if it did, it would turn into strontium 88. There's our simple math, right? 88 plus 4 is 92. 38 plus 2 is 40. You're done. It's an alpha particle. All right, let's try one more. How about we do a beta negative decay of, how about we have boron 12. 12 over 5b is going to beta negative decay, 0 over -1 beta, negative, and 12 and zeros, 12. 6 carbon. It would turn into stable carbon 12. That's the beta negative decay of boron 12. A beta particle is 0 over negative 1. 6 and negative 1 is 5. 12 and 0 is 12. Done. This is the beta negative particle. Everybody with me? Remember that from yesterday? Okay. And let's do a beta positive decay of beryllium 7. 7 over 4 beryllium. Yesterday I accidentally took my one good marker home. That's why I'm doing this. 7 over 4 beryllium. It's going to beta positive decay. 0 over 1 beta plus. And let's see, 7 and 0 is 7. What and 1 is 4? 3. That would be lithium. So the beta positive decay of beryllium 7 will give us lithium, stable lithium, because isn't lithium normally, oh, I can't get it over there. Isn't lithium normally 7? Isn't that what lithium normally is? Number 3 on the periodic table, 6.941. So the beta positive decay of beryllium 7 would turn into stable lithium. And there's our 3 examples. Now, if you notice here, here's a nuclear power plant. Do you see this coming out here? Do you know what this is? Yeah, it's not, though. You know what it really is? It's steam. It's just water. Nuclear power plants don't give off any smoke or anything that. Not like a coal power plant. They use water inside the plant to cool off other water that has been turned to steam to run basically just a steam-powered turbine. All nuclear power plants are doing is really just boiling water. Instead of using coal to boil the water, they use the heat from nuclear fission, all right? So the power plants, though, are concrete. 1, to make them strong. 2, to prevent any decay. And then the last thing I'm going to tell you from these notes is that, tell you what, I'll leave this for the next little thing. All right, and we're out, people.